Welcome to the second lecture in EE381. So today's lecture is going to be related to the Laplace transformation. So while representing the systems, we are usually going to be using the Laplace transformation. So here, suppose that we have a simple mass system here with mass value equal to m kilograms. Then suppose that we have some friction here represented by the friction coefficient b, and suppose also that I have a spring here that is connected to a fixed point, and there I have the spring coefficient k. In the next part of the course, we are actually going to be trying to model such systems. Of course, when I talk about a system, I need to define what it is input and output are. So here I have the input, which is the force F, and suppose that I have the output, which is the position of the mass from an equilibrium point here, which I show as y. So y is the displacement of the mass from an equilibrium position in this system. In the mathematical modeling part of this course, we are going to learn how to mathematically model such a simple system. We are going to see actually more complex examples as well. So here, let us write the mathematical equations. Here, it really doesn't matter if you don't understand what I write here, but you just have to think about in terms of some expressions. You don't have to understand how we obtain such expressions. So it is m times y double dot is going to be the net force applied onto the mass, which is Newton's second law. And I have here F minus, I have B times y dot minus K times y. Okay? This is called the differential equation representation of this system. And in general, it's going to be very, very difficult to deal with differential equations with different orders. Instead, we are going to be passing such systems into Laplace domain, and we are going to represent the system in Laplace domain. So we're going to have a Laplace domain expression representing a system. The relationship between the input and the output of the system will be represented by a function of s. So in order to be able to do that, I'm going to pass such an expression into Laplace domain, and this is going to give me m. Instead of the second order derivative, I will put s squared, and I will put it as Laplace transform of y here. And instead of f of t here, which is a function of time, I would put its Laplace transformation minus b times y dot is going to be s times y of s, and I would have minus k times y of s here. We are going to see how I can obtain actually such an expression. While trying to obtain such an expression, I assume that the initial conditions of the system are all equal to 0. There are two initial conditions, and both of them are equal to 0. And then what I'm going to do is that I'm going to try to write something called a transfer function. And this transfer function is going to be the ratio of the Laplace transforms of the output to the input. Okay? So I would have here y of s, and I would have here f of s. This is called the transfer function mathematical model for the system. And it is a Laplace domain quantity because these quantities y of s and f of s are the Laplace transforms of these functions f of t and y of t. Okay? If you actually obtain f of s, y of s over f of s from this equation, you're going to see that it's going to be something like this. 1 over ms squared plus bs plus k. This is a second order mathematical model in Laplace domain for the mass spring friction system that we started with. So we are going to use such transfer functions extensively. And actually, most of the time, we won't even write the differential equation corresponding to this transfer function. We are going to start with the actual transfer functions like this. So that brings us the the thing that you have to be able to actually interpret such a Laplace transformation, what it means. And in this lecture, we're going to try to understand what type of function of time we have with this Laplace transformation. Okay? Here you see that the Laplace transformation turned the differential equation into an algebraic equation. There are no longer derivatives in this equation in Laplace domain. There are only multiplications with s, with y of s, etc. So Laplace transformation actually turns the differential equations, linear time invariant differential equations, into algebraic equations without any derivatives. So that is why we are using the Laplace transform. That is the inherent idea here. And then what we are going to do is that I'm going to represent this system with a single block, with its transfer function is here, g of s, and I have the input signal here, and I will have the output signal here. Okay? But first we are going to review the Laplace transformation in order to be able to understand, in order to be able to give some meaning to such functions. And you will see that when I look at such a function, everything depends on the roots of the denominator here. The roots of the denominator of a Laplace transformation are called the poles of that Laplace transformation. Okay? And we are going to see that the time function that is represented by this Laplace transformation will be dependent on the roots of the denominator polynomial, which is ms squared bs plus k. We are going to see that when we have complex roots for such a transfer function, then the time domain function here will be oscillatory. It will include sines and cosines. And when we see that the roots of the denominator here are actually real, we are going to see that we will encounter just exponentials, either decaying exponentials, growing exponentials, etc. So whether the roots of this denominator are complex or real will determine the time function that we are going to encounter. So let us start with the review of this important concept of Laplace transformation. I'm going to start with the definition of the Laplace transformation. Then we are going to use this definition in order to be able to obtain some important Laplace transformations. So let us say the definition. The Laplace transformation of a function of time. I will show the Laplace transformation with the letters LT of a function of time This function is going to be shown by f. So strangely, this is my letter f, so I hope you will get used to it. So this is f, and there is a dot here. This is a function of time. So instead of the dot, I will substitute t, and that is going to denote the value of the function at time t. But this notation will show just the overall function here. And this function is defined from non-negative real numbers to real numbers. Okay? So I have this function which is defined over non-negative time instance into real numbers. Is given as, so I have this Laplace transformation. When I have small f as the function of time in time domain, I will have capital F as the Laplace domain quantity. It's Laplace transformation. So this is going to be from 0 to infinity f of t e to the minus st dt, where s is a complex number. So S is an element of the set of complex numbers. All right? So S can have imaginary parts. So it really does not have to be a real quantity. So this is a definition. So the Laplace transformation is defined with an integral, and sometimes it is going to be very, very easy to evaluate such an integral. So we will be able to calculate the Laplace transforms of some functions quite easily, and sometimes the integral definition is going to be difficult to evaluate, and we are going to be using properties of this Laplace transformation. And in this lecture, we are going to see the properties as well. So here, we will show that we show the relationship between f of t and f of s as, so I show that f of t has a Laplace transformation capital F of s using such a notation with an arrow here. Sometimes I will put here the capital L in order to show that this is a Laplace transformation relationship. All right? So we are going to start with an example. So probably the most important example that we are going to see in this course, the most important function that we are going to see is going to be the unit step function. So it is unit step function. There's a C missing here. So this function is going to be looking like this. So I have the time domain here, t. The function is going to be equal to 1 everywhere. For every non-negative number here, the function is going to be equal to 1, and for negative time instance, it is going to be equal to 0. As you see, for this Laplace transformation definition, the values of the function before time t is equal to 0 for negative time instance is not really important. So therefore, we are always going to be assuming that for negative time values, the functions that we are working with are equal to 0. All right? So that is our assumption here. And this is called the unit step function. And the reason is maybe obvious. So this is looking like a just step of a stair. Okay? So it goes from 0 to 1 at time t is equal to 0. Its value is equal to 1 at time t is equal to 0. So now let us try to find the Laplace transformation of this function. And in this case, it is very easy to evaluate this integral. So I will show f of t, I will show the step function as the function small u of t here. And let us try to write the integral here. So this is equal to 1 for all non-negative time instance. That is the unit step function. So most of the time in this course, we are going to use the unit step function as an input to a system. So here, in the mass spring example that I have just erased, we are going to give the step input to it, which means that I will choose the force f of t as this function. So force is going to be equal to 0 for negative time instance, and force is going to be 1 newtons for positive and 0 time instance. So unit step will be actually used as an input to our systems in most of this course. So here let us calculate the Laplace transformation of the unit step. F of s is equal to, I will just use this definition. Here the integral is from 0 to infinity, and I will replace f of t with just the value of the unit function, which is equal to 1. Then that is going to leave only e to the minus st here than dt. So this is going to be 0 to, infinity. I will have e to the minus st dt. Okay? let us take the integral of e to the minus st with respect to t. It is going to be minus 1 over s e to the minus st evaluated from 0 to infinity. Okay? And you see here that I have minus 1 over s, minus 1 over s is just a scalar here with respect to t. So I have e to the minus st as t goes to infinity is going to be equal to 0. And e to the minus st as t goes to 0, it's going to be equal to e to the 0, which is equal to 1. So I would have this one, which is going to give me just 1 over s as the Laplace transformation. So that means that the unit step function f of t is equal to 1 for t larger than or equal to 0 has the Laplace transformation f of s that is equal to 1 over s. All right? This might really look strange here because the function 1 is really a very, very simple function. But 1 over s is really not so. So here, somehow, this simple function turns into a complex thing at the end of the transformation. So what its use can be in such a case. So we're going to see that its advantages will overcome its disadvantages, which Laplace transformation looks like a disadvantage here in terms of simplicity, but we're going to see that it has much more advantages than disadvantages like this. So here, this was the first function. When we see a Laplace transformation, most of the time we will be interested in its poles and zeros. So I'm actually going to be defining poles and zeros of a Laplace transformation. Poles are going to be the roots of the denominator, and zeros will be the roots of the numerator. And actually, after we define poles and zeros, we will see that this Laplace transformation has no zeros because the numerator never becomes equal to 0, and it has one pole at the origin, s equals to 0. Okay? So this Laplace transformation is a ratio of two polynomials. I will write here this one as n of s divided by d of s. And in this case, n of s is just equal to 1. Numerator polynomial is 1. And the denominator polynomial is s. And then we are going to be looking at the roots of these polynomials. Roots of this polynomial. What is the root of a polynomial? Root of a polynomial is the value of the argument of the polynomial at which the value of the polynomial is equal to 0. So when is n of s equal to 0? For which s value n of s is equal to 0? It is for no s values it is equal to 0. Therefore, here this Laplace transformation will not have any zeros. I will call the roots of n of s as the zeros of this Laplace transformation, and I will call the roots of d of s as the poles of this Laplace transformation. And what about the denominator? Denominator is a very simple polynomial, and when I equate the denominator to 0, I see that at s equal to 0, this denominator polynomial, the value of the polynomial is equal to 0. Therefore, I can say that the denominator has a root at s equal to 0. And that means that this Laplace transformation has a pole at s equal to 0. Okay? But let us first, before defining the poles and zeros, I will first solve one more example which is going to be useful. So here the example is going to be f of t, which is equal to e to the at for t larger than or equal to 0. Okay? So here a can have different signs. A is a real number here. A can be equal to 0, a can be positive, or a can be negative. And in each case, the behavior of this function changes. So let us look at the behavior. So this is time here. And at t is equal to 0, this function is always equal to 1. A to the 0 is 1. So if a is equal to 0, this function is a constant at 1. All right? So this is the value 1. So this is the case when a is equal to 0. When a is positive, as t increases, this function is increasing exponentially, obviously. And if a is negative, then the function is decreasing exponentially towards 0. All right? So this is the case when a is larger than 0, strictly larger than 0. And this is the case when a is strictly smaller than 0. But the values of these functions are all equal to 1 at t is equal to 0. All right? So here we are wondering about what the Laplace transformation of this function would be. And I know the answer when a is equal to 0. Because when a is equal to 0, this function is nothing but the unit step function. And as a result, its Laplace transformation has to be 1 over s at when a is equal to 0. But what about the other cases? Let us try to look at this. So I have f of s is equal to, I will use the definition once more. So it is from 0 to infinity. Instead of f of t, I will choose e to the at, and I will have e to the minus st dt here. Okay? So now I will write this, the multiplication of these two exponentials, I will write it as a single exponential from 0 to infinity, e to the minus s minus a t dt. So you see that this is going to be e to the minus st and e to the minus at, which is e to the at. All right? But I have just calculated an integral just like that. So, which is a very, very similar integral here. I have just calculated this one. And now I need to calculate just this one. You can try to take the integral again as I did there, and then evaluate the integral at the limits. But here I see that the difference from here to here is nothing but I change s into s minus a. Okay? So therefore the result here should be what happens when I change s here with s minus a. So this is going to be just 1 over s minus a. So I have found one more Laplace transformation, and what about its poles and zeros? I can actually examine poles and zeros of this Laplace transformation as well. So here I have seen that e to the at for non-negative t values has the Laplace transformation 1 over s minus a. And in this case, this Laplace transform, the numerator polynomial is 1 again. N of s is again equal to 1. So this Laplace transformation does not have any zeros. And this Laplace transformation has a pole at s equals to a, at the real number s equals to a. So in general, we are going to work with Laplace transforms in the form of a ratio, in the form of a ratio of two polynomials. In S. Remember, S is a complex number. And this Laplace transformation is going to be looking like this. F of s is equal to, I have b0s to the m plus b1s to the m minus 1. These are going to continue until bm minus 1s plus bm. So these are the coefficients of the numerator polynomial. B's are those. And I will have a denominator, s to the n plus a1 s to the n minus 1 going until an here. So I'm going to be writing this ratio of the polynomials again as these polynomials. So n of s is going to be the numerator polynomial, and the denominator polynomial is going to be called d of s. All right? And then I'm going to be equating d of s to equal to 0 and solving for s values which satisfy this equation. All right? And that is going to give me the roots of the denominator. And these are called poles of f of s. Okay? So this is a Laplace transformation, and roots of the denominator polynomial will be called poles of f of s. And when I look at the numerator polynomial, roots of the numerator polynomial, these are going to be called the zeros of f of s. So think about how many poles and zeros such a transfer function would have. We know that if we have an nth order polynomial, then it's going to have n roots. That means that this transfer function would have n poles, and it's going to have n zeros, right? So here, number of poles is n, order of this polynomial, denominator polynomial, and I would have the number of zeros is equal to m. Okay? So when I look at an example here, f of s, I have just calculated this f of s, 1 over s minus a, then n of s is equal to 1 and d of s is equal to s minus a, and therefore I would have no zeros for this Laplace transformation, because the numerator polynomial is never equal to 0 for any value of s, but the denominator polynomial becomes 0 when s is equal to a. So this Laplace transformation has one pole. In general, these Laplace transformations will be transfer functions, a mathematical model that I showed at the beginning of the lecture. That is why sometimes I am actually saying transfer function instead of Laplace transformation. But let us think about these now just as Laplace transformations rather than transfer functions. So then I can talk about poles and zeros of Laplace transformations. Similarly, we will be talking about poles and zeros of transfer functions. So here, when we actually calculate the poles and zeros of a transfer function, we usually look at a pole zero map of that transfer function. Pole zero map is nothing but showing these zeros and poles of a Laplace transformation on the complex plane. So I have real of s and imaginary of s here, and this is the complex plane. And in this case, this Laplace transformation has no zeros, so I don't really have to show anything for zeros. And for poles, I need to show s equals to a. Suppose that a is positive, then I will mark the point s equals to a here. I assume that a is a real number and a positive real number. So in that case, I would have such a pole zero map. So here, this is either called as pole zero plot or pole zero map. Of course, we are going to see much more complicated Laplace transformations, like the following. Suppose that I have a Laplace transformation s plus 1 divided by s squared plus 2s plus 2. Okay? This is a more complicated Laplace transformation. And let us look at its poles and zeros. So its numerator polynomial, n of s, is s plus 1. So we see that it's a first order polynomial here. Therefore, it has one root. And that is going to be at s equals to minus 1. I will equate this thing to 0. And s equals to minus 1 is going to be just a 1, 0 of this Laplace transformation. And d of s is s squared plus 2s plus 2. Of course, you must know how to find the roots of a polynomial. Here in this course, I will generally try to do the following. I will try to complete this polynomial into a full square. S squared plus 2s. Then what should I add to this s function in order to be able to make that a full square of a complex number? S squared plus 2s plus 1 here is going to be s plus 1 square. Okay? But on the left hand side I have 2, so I will just add one more here. Alright? So that is going to be s plus 1 square plus 1. And I need to find the roots of this polynomial, and it's going to be the following. So I will equate this thing to 0, and this is going to give me the poles of this Laplace transformation. And how many poles do we have? In this case, to answer this question, I will just look at the order of this polynomial, which is equal to 2. So this Laplace transformation has 2 poles. So here, I can actually try to solve for s in this equation. S plus 1 squared is equal to minus 1. And I will take the square root of both sides, which is going to give me s plus 1 is equal to square root of minus 1. So this is going to give me a complex number, and this is going to be the plus or minus the complex number I here. All right? And when I solve for s, then that is going to give me a minus 1 plus minus I. So these are the poles of this Laplace transformation. So the interesting thing about electrical engineers is that they are not using this letter I for the complex number square root of minus 1. I know it really sounds stupid, but in electrical engineering we are showing the number I with J. Okay? Very, very original. So this is so J is the same thing as the square root minus 1. The story is that the electrical engineers are using I for the current variables, electrical current. So that is why they're using this number J for instead of I. It's a stupid excuse, I think. So here, let us make a pole zero map of this transfer function. So I have, in this case, 2 poles here, and I have 1, 0. So this is my complex plane, and my single zero is at s equals to minus 1. We show the zeros with the letter O here, just a small circle, and we show the poles with cross signs like this, as I did in the previous example. So the real part is minus 1, and the imaginary part is plus or minus j. So this point is j, this point is minus j, and this is the imaginary part. So I have 2 poles located at the complex conjugate locations here, -1 plus minus j, and I have a single 0 located at -1. All right? So this finishes the introductory ideas with the Laplace transformation. Now we're going to be looking at the properties of Laplace transformation. Most of the times, we really cannot directly see what type of function of time a Laplace transformation would correspond to. That is why we are learning these properties. By learning about these properties, when we look at Laplace transformations, like this, for example, we are going to be able to understand what type of time function such a transformation would correspond to. And when I look at such a function, I just concentrate on the denominator. And in the denominator, my poles are at -1 and plus minus j. So at the end of this lecture, you need to be able to understand what type of function of time such a Laplace transformation would correspond to. So what is f of t? What is f of t looking like? All right? And here I will just give you the quick answer. F of t is going to be looking like something like this. So I have a -1. This negative real, you will not understand this now. We're going to see the properties later. But by just looking at the real part -1 here, I will understand that the time function f of t is actually decaying. Okay? It is going to be decaying towards 0. It might be non-zero somewhere here for small time values, but it's going to decay to 0 because of this -1. And because of this imaginary part, I understand that there will be oscillations in the function. Okay? So in f of t, there will be sine and cosine functions somehow. So if I just draw a very, very rough representation of f of t, it's going to be looking like something like this. Okay? And I can actually understand this just by looking at the pole locations of this function. Pole locations of this function. If the pole locations are in the left half plane, we are going to see that the functions should decay. We will see that if the pole locations are in the right half plane, then we will see that the functions will be growing as time goes to infinity. We will see that if some poles are imaginary, we will see that there will be oscillations. Okay? If all poles are real, we will see that there will be no oscillations in the function. And we will be able to do that by just looking at the Laplace transformation. We will understand what type of function f of t is by just looking at the pole locations. So here let us write some important properties of Laplace transformation. So here in this discussion, I'm going to call a function f of t with a Laplace transform f of s, and have a function g of t with a Laplace transformation g of s. Okay? And let us look at the first property, which is the easiest. So Laplace transform of a function a f of t plus b g of t is going to be, so Laplace transformation of a linear combination of two functions will be the same linear combination of the Laplace transformations of these functions individually. Okay? So this can be just proven by using the integral definition. And this is nothing but a times f of s plus b times g of s. So you see here this letter L, and the parenthesis shows the Laplace transformation, And Laplace transformation of f of t is f of s, and Laplace transformation of g of t is g of s. So when I have a linear combination of two functions, when I take the Laplace transformation of that linear combination, then the resulting Laplace transformation is nothing but the same linear combination of the individual Laplace transforms of those functions. Okay? This is a very, very nice property, and actually I can divide this property into two parts. This single property, I can divide it into two parts. So the first part is, the name of this property is linearity. Okay? Linearity of Laplace transformation. And in general, linearity is composed of two parts. The first part is called the homogeneity, and it is this property. So when I have a single function, this property is true for any a and b. So I can just take b equals to 0, and that is going to give you this property. So when I take the Laplace transformation of a constant with respect to t times f of t, that Laplace transformation is going to be that constant times the Laplace transformation of f. Okay? This is called homogeneity. Homogeneity property. The second property that is giving us linearity is the additivity. So when I have two functions, f of t and g of t, when I add those functions and take the Laplace transformation of the addition, then that is going to be the addition of the individual Laplace transforms. Plus Laplace transform of g of t. So this is equal to f of s plus g of s. And this property is called additivity. And linearity is a combination of these properties. When both of these properties are satisfied, we can show that the Laplace transformation is linear. And it is actually linear, and it satisfies this property for any constants with respect to t, which are a and b here. Okay? So this actually gives us a way to calculate simple inverse Laplace transforms. So let us look at examples. So suppose that f of t is equal to 2.1. Okay? F of t is equal to a constant. And this is true for positive, non-negative t values. What is the Laplace transformation of this thing? It should be very easy by using the linearity, because in this case, f of t is nothing but 2.1, a constant, times 1 for t larger than or equal to 0. And I know the Laplace transformation of 1, which is the unit step function, which is 1 over s. And since this function is multiplied with 2.1, its Laplace transform should be multiplied with 2.1. As a result here, f of s is going to be Laplace transform of unit step is 1 over s times 2.1 over s. Let us look at a second example. So I have minus 5 plus 3 e to the minus 2t. And this is true for non-negative time instance. So what is the Laplace transformation of such a function? So you see that this is again a linear combination of two functions I know the Laplace transforms of. Okay? So it is minus 5 times 1 unit step and 3 times e to the minus 2t, which is the exponential. I know that the exponential e to the at has the Laplace transformation 1 over s minus a. Okay? And here what is a? If I show this e to the minus 2t as e to the at, what is going to be a? A is going to be just minus 2 in that case. Since the Laplace transformation of e to the at is 1 over s minus a, and I have a is equal to minus 2, then I will have the Laplace transformation of e to the minus 2t is equal to 1 over s plus 2. All right? So let us write the Laplace transformation. F of s is going to be minus 5 times 1 unit step, minus 5 times 1 over s. And I will have plus 3 times e to the minus 2t, which has the Laplace transformation 1 over s plus 2. All right? So you see that this simple property of linearity allows us to calculate some more complicated Laplace transforms of some functions. Let us go into the second property. The second property is going to be probably the property that we are going to use most. So you are given a function f of t, and you know its Laplace transformation, capital F of s. What would be the Laplace transformation of its time derivative? So we will be asking this question. So the second property is this. Laplace transformation of f prime of t. Here f prime of t denotes the first order derivative of the function with respect to t. Okay? So this is Laplace transformation of d over dt f of t. This is f prime. That is given as s times f of s minus f of 0. So this is the property here. And what does it say? When you know the Laplace transformation of a function as f of s, you can write the Laplace transform of its derivative directly by multiplying that original Laplace transformation with s and then subtracting the value of the function at t is equal to 0. Okay? So this f of 0 is the value of the function, the value of f of t at t equals to 0. Okay? So this actually allows us to calculate Laplace transforms of more complicated functions. So let us look at an example. So the first example that I'm going to solve is going to be very, very easy. So let us say that f of t is equal to e to the 2t. Okay? Then you can tell me that we have already seen what the Laplace transformation of this thing is. It is f of s is equal to 1 over s minus 2. Okay? So sometimes I'm forgetting here to write t larger than or equal to 0. In this course, we are going to have the definitions of functions always t larger than or equal to 0. Okay? Even if I forget, you need to put them. So the bad thing about having lectures like this, now I'm in a meeting room in our department. Time is 10 o'clock in the evening. And obviously I don't have any students here. So that is the bad thing here. So I cannot get any feedback here. So generally when I lecture, I look at the eyes of the students and try to see if everything is going correct or not. Here I don't know that opportunity, unfortunately. So please be patient, and if I make a mistake somewhere in any lecture, please let me know so that I can actually send an email about such a mistake in the lecture, or let you know that I made a mistake somewhere in the lecture. Okay? So here we have this Laplace transformation here. So what is the derivative of this function? F prime of t is going to be the time derivative of this function, and it's going to be 2 times e to the 2t. So do I have to really use the property here? Do I really have to use the property there in order to be able to know the Laplace transformation of twice e to the 2t? I really don't have to use this derivative property here, because this is nothing but this function times 2. From the first property, I know that the Laplace transformation is just going to be here. Laplace transformation of f prime of t is just going to be 2 times this f of s. Okay? 2 over s minus 2. But here, just in order to be able to understand, I will use also the property here, the derivative property, how this can be used in order to be able to obtain the same result here. Okay? So now let us write s times f of s minus f of 0. So I have s here. F of s is 1 over s minus 2, 1 over s minus 2, and I would have here minus f of 0. Okay? So f is here this function. That is why I need to evaluate this function at t is equal to 0. So this is going to be just equal to 1. Okay? F of 0 here, substitute t equals to 0, and it's going to be 1. All right? So here this is equal to s over s minus 2 minus 1. It is s minus 2 over s minus 2. There is a plus here. And s's are going to cancel. This is going to be twice 1 over s minus 2. Okay? So you see that we get the same result here. So this property holds for all differentiable functions that we have. So here we are going to be able to use this property, this derivative property, in order to be able to calculate some Laplace transforms of complicated functions. The first function that I'm going to use is going to be the sine omega t. So let us say that f of t is equal to sine omega t for t larger than or equal to 0. And the question is, what is f of s? What is the Laplace transformation of this function? So here I'm going to be using this derivative property here. And I'm going to take the derivative of sine omega t twice. I know that when I take the derivative of sine, it becomes a cosine. And when I take the derivative of cosine, the second derivative of sine, it again becomes a sine. Okay? I'm going to use this derivative property and this property here in order to be able to calculate the Laplace transformation of sine omega t. Okay? So I know that sine omega t, this is f of t, has the Laplace transformation f of s. Currently, I don't know what capital F of s is. That is my aim here. I need to calculate capital F of s, and I don't know it. So that is why I'm making this derivation. Let us look at f prime of t. It is the time derivative of sine omega t. It is going to be omega cosine omega t. Okay? And according to the derivative property there, what is going to be the Laplace transformation of this first order derivative? It is going to be s times the original Laplace transformation, f of s, minus f of 0. Okay? And what is f of 0? So I will substitute t equals to 0 here, and sine 0 is 0. Okay? So this derivative then has the Laplace transformation minus f of 0, and this is equal to 0, which is going to give me s times f of s. I still don't know what capital F of s is, but when I look at this relationship, the Laplace transformation of this thing should be s f of s, when the Laplace transformation of sine is f of s. Okay? Now, I will take the derivative once more. F double prime of t. Now, this omega is a constant with respect to time, so I take the derivative of only cosine omega t, which is going to be minus sine omega t times omega. So I have omega square, and I would have a minus sign here, minus omega square sine omega t. Okay? So you see that I get again the sine omega t term once more. And now I know what the Laplace transform of this thing should be. Okay? What should it be? It is a constant times sine omega t. So the Laplace transform of this function should be f of s times minus omega square. Okay? But let us use the derivative property first. This second order derivative is the derivative order of the first order derivative. Okay? Second order derivative is the derivative of the first order derivative. So here I can definitely use that property. I can substitute here f double prime, and this is going to be the f prime. This is going to be the Laplace transform of f prime, and this is going to be f prime evaluated at 0. Okay? So now let us write this. So this is the derivative of the first order derivative. So therefore its Laplace transformation is going to be s times Laplace transformation of f prime, which is s f of s. That is going to be s square f of s, minus the value of the function at 0, f prime of 0. Okay? I used here the derivative property on second order derivative. Since second order derivative is the derivative of the first order derivative, here I can use this property by replacing f with f prime. Okay? And what is this? F prime of 0. It is this thing. Cosine 0 is 1. So this is going to be just omega. Okay? So that is equal to s square f of s minus omega. But I know that this function is nothing but minus omega square sine omega t. So this is a constant with respect to t times the sine function. So its Laplace transformation, according to the linearity property, is going to be this. This is again the same Laplace transformation, minus omega square f of s. Laplace transformation of sine is capital F of s, and this is minus omega square times f of t. As a result, the Laplace transformation of this thing should be minus omega square times f of s. So these two Laplace transformations should be equal. Okay? And from that equality, I can try to solve what capital F of s is. So it is minus omega square f of s is equal to s square f of s minus omega. Okay? Take the omega to the left. Take minus omega square f of s to the right. So I would have s square plus omega square times f of s is equal to omega. So then from this equation I can solve what capital F of s is. Okay? It is going to be omega over s square plus omega square. All right? So here I have used the derivative property to actually calculate the Laplace transformation of sine omega t. Now what about cosine omega t? How can I calculate its Laplace transformation? I can actually use the same derivation here. I can actually start, instead of sine omega t, I can start with cosine omega t and call its Laplace transformation f of s. And then I can take its derivative, which is going to give me sine here, minus sine here. And then I will take its derivative, which is again going to give me a cosine. Okay? And then I can use this type of idea to calculate the Laplace transform of cosine omega t. Please try to apply that as an exercise. Here I'm going to go in a different way instead. So let us say g of t is equal to cosine omega t. Okay? What is this is again t larger than or equal to 0. What is capital G of s? We are wondering about this. And here I'm going to use the second step of this earlier derivation. So you see that I have a Laplace transform pair here. Omega cosine omega t has the Laplace transformation s squared times f of s. Sorry, s times f of s. Okay? S times f of s. And I have just calculated what f of s is. So that is going to give me s omega s square plus omega square. Okay? So here I see the important Laplace transform pair. Laplace transform of the function omega cosine omega t is s omega divided by s square plus omega square. Okay? Then what is the Laplace transform of cosine omega t? So this is again a constant times cosine. Therefore, this Laplace transformation should be the same constant times Laplace transformation of the cosine. Okay? So I will divide both sides by omega here, which is going to give me this. This is the Laplace transformation of cosine. So now let us summarize. So sine omega t has the Laplace transformation omega over s square plus omega square, and cosine omega t has the Laplace transformation s over s square plus omega square. So in general, it is quite easy to remember for students this denominator, s square plus omega square. They always remember this thing, at least 90% of them. So students always remember this denominator for cosine or sine, but sometimes they mix this omega with s. Is sine in its Laplace transform, does it have omega or s? So most of the time that is, students are confused about this. The way I remember such thing, I of course memorize this. I don't do the derivation every time I need the Laplace transformation of sine or cosine. So the way I remember this is the following. So what happens when I substitute minus omega instead of omega in a sine function? Sine minus omega becomes minus sine. Okay? So as a result, when I substitute minus omega in a sine function, the sine should change its the sine function should change its sign, whether it's positive or negative. Okay? You see that when I substitute omega equals to minus omega, this Laplace transform changes its sign as well. So it's just multiplied by minus 1. What happens when I substitute omega equals to minus omega in a cosine? Cosine minus omega t is just equal to cosine omega t. Okay? Cosine does not change when I substitute minus omega into itself. Okay? So look at this Laplace transformation. When I substitute omega equals to minus omega, this Laplace transformation remains the same. Okay? So as a result, cosine should have an S here, and the sine should have an omega here, which makes its sign change when omega changes its sign. Okay, that is how I remember it always. So here we have found the pole zero maps of some Laplace transformations. Let us now find the pole zero maps of these functions. So pole zero map of sine function is going to be something like this. The function doesn't have any zeros, but it has some poles here. Okay? So let us find its poles. S squared plus omega squared is equal to 0. Then S squared is equal to minus omega squared. Take the square roots of both sides. Then you're going to have square root of omega squared is omega. Square root of minus 1 is going to be plus minus j. Remember, j is nothing but the number square root of minus 1. Okay? So I have S equals to plus minus j omega. I have two poles for this Laplace transformation and no zeros. So I have one pole here at j omega, another pole at minus j omega, and no zeros. So we see that for sine function, and we will see that it's for the cosine function, we have pure zero real part poles. Okay? So that is the characteristics of the sine and cosine function. They always come with imaginary poles. Alright? And when the sine function is not decaying or growing, those poles would always be exactly on the imaginary axis. They are not on the left half plane. They are not on the right half plane. They are exactly on the imaginary axis. Okay? When the sine is not growing or decaying, its amplitude is fixed. Alright? Let us look at cosine here. It has the same poles. It has the same poles here, j omega, and minus j omega here, but it has a 0, because the numerator is s, and it becomes 0 when s equals to 0. So it has a 0 at the origin. But this is an oscillation with constant amplitude, therefore it is coming with poles exactly on the imaginary axis. We are going to be able to understand that when these poles are on the left, being on the left for the poles are going to be very good. In that case, we will see that the amplitudes of these sines and cosines would be decaying. So I would have an oscillation, but its amplitude would be decaying when the poles are on the left and they are complex. And when the poles are on the right and I have non-zero imaginary parts, then I will see that the sines and cosines will be growing in magnitude. So there will be small oscillations first, but the amplitude is going to increase. So that is going to be something bad in a control system. So remember, I mentioned the concept of stability in the first lecture, and it is really a bad thing for a control system to be unstable. We will see that if we cannot design feedback systems in a good way, sometimes they can be unstable. And these instability can cause oscillations in a system with growing amplitude oscillations, with growing amplitude sine and cosine functions. So now let us look at a third property. The third property is going to be something interesting, and it's going to be easier to prove. So remember, I didn't give any proof for the second property, the derivative property. It is proof actually is not difficult if you remember some calculus concepts. If you remember integration by parts, some integration method that is called integration by parts, u, dv, etc. Then you can actually quite easily prove the derivative property, but I'm not going to give that derivation in this class. Instead, we are going to go into the third property. Laplace transformation of e to the minus at times f of t is going to be f of s plus a. So here I need to first explain what such a property would mean. So I have a function f of t and it has a Laplace transformation capital F of s. Okay? And I'm multiplying that function with an exponential e to the minus at. Depending on the sign of the exponential, we have this exponential either growing, decaying, or remaining constant at 1. Okay? And I'm multiplying this function f of t with e to the minus at. Then I'm wondering about the Laplace transformation of the new function that I obtained here. This is my function g of t, e to the minus at f of t. This property tells us that in order to be able to find the Laplace transformation of such a multiplication, all I have to do is nothing but substitute s plus a instead of s in f of s, the original Laplace transformation of the function. Okay? This is f of s plus a. All right? So from this simple property, you can actually obtain other properties. What would happen, for example, if I, instead of multiplying the function with e to the minus at, if I multiply the function e to the at, what is going to be the Laplace transformation in this case? You have to be looking at how can I turn this function into this function. If I substitute minus a instead of a in the upper function here, I would obtain minus a t, it's going to be e to the at. Okay? From the first function to the second function, I can pass by substituting minus a instead of a in the first function here. Okay? Then I will do the same here on the right. If I substitute minus a instead of a, I would get my Laplace transformation. So this is f of s minus a. So if you multiply a function with e to the at, then its Laplace transformation is going to be substitution of s minus a instead of s in the Laplace transform of the original function. Okay? So this is our property, and it's not really difficult to prove this property. So here, let us look at, let me call g of t is e to the minus at times f of t. Okay? Then what is the Laplace transform of g? It is capital G of s, and by the definition of Laplace transformation, it's going to be g of t e to the minus st dt. This is nothing but the definition of Laplace transformation. Okay? And then I will substitute the formula for g of t. G of s is equal to 0 to infinity. G of t is this function, e to the minus at f of t, and I still have e to the minus st here, dt. Okay? And I'm going to combine these two exponentials. It is going to be e to the minus s plus a times t. Okay? 0 to infinity f of t e to the minus s plus a t dt here. But what is this? If instead of s plus a here, if I had only s here, then it would be the Laplace transformation of f of t. Okay? And that means that this g of s is nothing but, in the Laplace transformation of f of t, I substitute s plus a instead of s. Okay? So g of s is equal to f of s plus a here. So here let us look at some examples. The first example is going to be a very, very simple one, and it is going to tell us some important thing that we have seen before. So remember the unit step function, f of t is equal to 1 for t larger than or equal to 0. I know that capital F of s is equal to 1 over s. Okay? Now remember the following. G of t is e to the at for t larger than or equal to 0. We have also found the Laplace transformation of such a function, and we have found that it is 1 over s minus a. Now you clearly see that there is a relationship between these two Laplace transformations, and that is nothing but I substitute s minus a here in order to pass from here to here. Okay? And why is that? Because e to the at is nothing but e to the at times 1. Okay? And you see here that if I use the property given like this, I need to substitute s minus a, and that means that I need to substitute s minus a here, which gives me this Laplace transformation. That is something that we didn't emphasize before. So now, first, maybe you don't need any break now, but I will need a break, and probably I will use my tea in that break, but it will be probably instantaneous for you. So I'm going to be breaking for 10 minutes, and then we'll start with the next lecture. Bye.